Okay, so we are going to continue. Sorry if the microphone is not quite as good here, but I'm trying to optimize this recording. Okay, so this is part 2. And okay, so suppose we have a document fourscore 7 years ago. This is the Gettysburg Address. We need to be able to create some kind of array of numbers, preferably of a fixed size, that we can now put into our machine learning model. So it's maybe a little bit more easy to understand with like CNNs, but with CNNs or with dense linear models, we have a fixed sized vector that represents our data, and it gets put into the machine learning model, and then let's say we're doing classification or text generation, whatever it is, an output comes out. Now the problem with text is, of course, it isn't fixed size. It could be long, it could be short, and it's made up of words. How do we represent this as a bunch of numbers in a consistent way? Now we've talked already about time series and RNNs, and we can think about this as a time series. So the fact that the overall length of the document could be different could be okay in terms of a time series, but we need to represent the characters, the words, or something as vectors, and we need to have these chunks that are machine learning algorithm can operate on. So the first thing we need to do is to create these chunks, and this is called tokenization. So there's different strategies we could have for tokenization. Obviously, text is made up of characters at the very lowest level. So we could break it up into characters, and then each chunk could be that character. Or we could somehow break it up into words. Of course, words have different length, but somehow we could consider each word as an atomic thing, as if it were a character. That word is different from another word, and those could be our chunks. Or sentences, like a whole sentence could be a chunk, or a whole document could be a chunk. So there's a trade-off here. If we go to the level of characters, then we're going to sort of have there's only, if it's lowercase, 26 characters, or 128 if we use, ASCII, or maybe Unicode will have more, but, we have a limited number of characters. And we have a lot of data, like a lot of repetition, which is good for statistics, right? So we have P comes up all the time. So our statistics are going to be more robust. That being said, that this is going to force our machine learning model to model all the relationship between characters. And that's going to be expensive. And that'll require more training. We'll have to have more parameters. So, our representation is easier, but the work that our model has to do and the amount of training we're going to have to do is going to be a lot more. On the other hand, if we work at the level of documents, what's great about that is that, all of the structure that we're interested in is incorporated. We have context, the whole document is, we have context of the beginning of the document and, all of the words and all of the sentence structure and everything is all encoded in there. So that's great. And so the model can use any kind of context. It doesn't have to like learn about how words are formulated or whatever. And there'll be a lot less parameters for training in some sense. But the number of documents that are possible is obviously like ridiculous, right? So it's a very high dimensional space. And it's really too hard dimensional for any kind of reasonable statistics. So that'll end up giving us data starvation. I mean, unless these documents are really tiny. So, usually we're looking at a compromise. Typically, we're thinking about our tokens being words. Now, a disadvantage with actually using whole words for our token size is that we'll have to fix a vocabulary in a language. So we'll have to, we'll be able to build our model for English or for French or for Chinese or whatever language we're using, but that'll be it. And we can't handle like weird words, like if a new word comes together, it's like a mix of other words or something like that. We don't have a symbol to represent it. Another thing we could do is we could use subword tokens. So by subword tokens, I mean if we had unpleasant, right? Then the un could be a subword token. And then we could have pleasant, or we could have ent. Lots of words have ent at the end. So we could break it into these little pieces that are almost like syllables that are called subword tokens. And that's good because with a smaller number of subword tokens than all the possible words, we could be able to express not just English but Spanish and French, other Latin character sets, and if we did the same kind of thing, at least at a phonetic level, maybe for Chinese or something like that, we could have those as well, or we could use pictograms. Subword tokens are becoming quite popular, and then actually somewhere between the two. Like we can take the most common words and represent those, and then everything else use the subword tokens. And that'll limit our vocabulary. We won't have as huge a vocabulary to deal with. But at the same time, we won't be forcing our model to be able to represent these words that are very, very common. And we can capture portmanteau and neologisms, Snowmageddon and different things that are like words that are put together. When you look at this kind of a thing, you see that there are these, words they're not just, by themselves, right? That there is this context of like a time series. So if you look before you, if you know English, idioms, it's leap. He who blank is lost, he who hesitates is lost, right? So there is a commonality in, given the context, the kind of words that fill in there. So one thing we could look at is not just words, but what's called n-grams. So we could group our chunks into, we could, if we wanted to go up from words, we could have we could represent our data in terms of these overlapping sequences. So we have like 4, maybe we're going to use 3 grams. So 4 score, and, score and 7, and so forth. It still preserves some of the neighborhood properties, so we still get some representation of that. But at the same time, it's not too big. We're not like dealing with whole sentences at once. So these are often used not so much for deep learning models, but for representations that we'll talk about in a second that are kind of shallow models. So we have these tokens. We've now broken the thing up into these tokens, but we have to represent these as numbers. Remember, we have to make them into some kind of vectors. So the way we're doing that is we have what's called a vocabulary. So you could think about, if let's say we were going to do words, that we would have a dictionary, and we'd have like, the first word, the second word. These are just, the beginning words in the dictionary. And we could replace the word by the index of the word. We could keep the vocabulary separately, but now instead of having to, kind of store the whole word, we could just store the index of the word. Now, there's a couple of problems with representing these by these numbers. Actually, actually feeding the machine learning algorithm these numbers. First of all, 20 is close to 21. A basing is close to a bait. They have nothing to do with each other as words, but as numbers, they're close together. So one problem with representing them literally as integers is that if we did, there's an assumption that the machine learning algorithm is likely to get confused about and think that numbers which are close together are somehow related, and that's just not true. So instead, we would likely use one-hot encoding. Now, one-hot encoding, if you remember, the number 1 is represented as 1 0 0 0 0 0 0 0 0 0. So, going back to here, we might have 80,000 words. So we'll have a vector that has 80,000 dimensions, and then, the first word is represented by a 1 and zeros everywhere else. The second word is represented as 0, 1, and so forth. Now, the good news here is that we've overcome this integer problem that one word is close to another because the numbers are close together. All of these distances are equal to each other. So we've turned these into categorical labels. They have no intrinsic similarity in terms of their distances. That's not necessarily a good thing, because their words are related, and we would like to capture that too. But at least we could start out with text. We could, do some pre-processing, remove, maybe remove punctuation, or maybe tokenize the punctuation and get rid of capitals, and then turn it into tokens, and then turn it into indexes, and then do our one-hot encoding. But it's still not optimal because, again, we know that words have some relation to each other, and these are like 80,000 dimensional vectors, which are, so quite big. We'd like to have some dimension reduction to maybe get them down to a more reasonable size, and we'd also like the way that these vectors sit in the space, which is called the embedding, is related to, words that are closely related should be close together somehow. Okay, but we'll get to that embedding in a little bit. So the first thing we can do is we can do, so words could be n-grams, or they could just be words. And the first representation, which is common for things like topic modeling. If we have paragraphs or documents which are long-ish, like maybe a few paragraphs long, little news stories and things like that, we can get a pretty good idea of what the topic that this story is about by just counting the number of representing the words that appear in this story and counting how many times they appear. So, if we see the word baseball and bat and most valuable player and runs, we know it's a story about baseball. And if we see like election, party, Democrat, Republican, primary, then we know that it's probably about politics, and so forth. So a way to represent this is what's called a bag of word model. The bag of word model just says, let's forget about the word order entirely. Let's just count up the number of times each of these vectors appear. We can make a vector like if that first word appears twice, it could be 2, 0, 0, 0, just with these counts. If the first 2 gram appears, we'll do 2, 1, 2, 0, 0, or 3, 0, 0, how many times that pattern appears, and we just count them up. And this is called the bag of words representation. And we don't even have to store the whole vector. We could remember the index with as a dictionary. We could have like what's called a sparse representation, which says it's the first index, and it has a 2 in it, and then third index has a 3 in it, and all the rest of them are zeros. So there's an efficient way to store this kind of vector. And then we could compare stories by a measure that sort of sees how often, what is the overlap? What are the words which appear in both stories? How much overlap is, and by measuring the overlap and how similar the counts are, we can get some notion of similarity between documents, and we can start to do things like clustering to find topics. Now, one of the problems with this straight word count, where we just count up the number of times a word appears, and we just do this word, is that there are these words like the and in, which appear a lot. We could remove those. Those could be stop words. We could remove those. But even so, there are words like maybe run, which come up in political articles, and they also come up in sports articles on baseball, for example, or in track, or they may come up in like somebody could have a run in their stockings. So this is a word that comes up a bunch of times in different contexts. It's a pretty common word, so it may not be that distinctive, but it's not a stop word. We do want to count it somehow. So there is a technique called TF-IDF. And the idea of TF-IDF is that rather than represent the count literally, what we'll do is we'll count the term frequency, how often this token or this word comes up in a document. But we'll also count the frequency that the word shows up in general in the collection of documents. So there's a kind of a universe of documents that we're looking at. This might be all of Wikipedia. And we want to characterize the topics in a particular Wikipedia article. So the TF part would be taking the words in a particular Wikipedia article, and then we're comparing that with the frequency of each of these words in all of Wikipedia articles. And so that's the IDF part. And so this is a normalizing factor. And then when we multiply these together, we reweight. So if a word is extremely common, it has to appear much more for it to be distinctive in that document. And if a word is not so common, then in the corpus, then it doesn't have to appear as much to be kind of important. So this gives us a feature sort of vector. So instead of having like the word, it's 0 if it didn't appear at all, and then it has this number, this TF-IDF number, instead of the count, that appears associated to the index of that word. And so we could turn that into a sparse vector, and so we could use the sklearn TF-IDF vectorizer, and then we have our training document, which is our corpus of all of our documents. We do a fit transform on this, and it on this vectorizer, the TF-IDF vectorizer, and that will transform it into into a collection of documents which are now represented as vectors. We do the same thing for the testing, and then we could set up a pipeline where we have our so this is how you would use just the vectorizer. But if you wanted to put it in a pipeline, you put it in a pipeline like this, where you've got the TF-IDF sort of as a pre-processing step, and then some classifier, it doesn't matter which one. Here it's a stochastic gradient descent classifier, essentially with logs, so I think it's a logistic regression essentially. And so, one follows the other, and then once you have a pipeline, you can do your fit and your train, and then, predict and so forth. So this might be your baseline. And then you would do maybe a deep learning model, to compare, you'd be able to compare it with the baseline. As an example of how you would do this bag of word model for, I think this is a sentiment and a text classification. And all the steps, I'm going to recommend this notebook. I'm not going to go through it now, but I recommend this notebook that is in Google Colab, and it's for PyTorch, so you can see, and it uses NLTK as its pre-processing rather than spaCy or scikit-learn, but it's all sort of in there, so you can try it and run it, and then change out the example they're giving and try it with different text. So as I mentioned, that this one-hot encoding is okay, and we can use it particularly for doing bag of word models, but these are really long vectors. So if we treat them actually as vectors rather than in the sparse representation, let's say because we want to feed it into a deep neural network, it's going to be kind of tricky, right? Because we'd have to have a huge number of neurons at the beginning to read our input vectors. A lot of weights. So we'd like to be able to reduce it. We'd like to, and it would also be helpful, again, like I said, if somehow the words that were similar, like run and walk, would somehow be close together. So this brings us to a notion of embeddings. And so we want to encode our words in a way so that they have the semantic meaning is somehow captured rather than just being 100 in a dictionary. So how do we do this? We're starting out with, let's say, the top 20,000 words, whatever, We were in 20,000 dimension. And let's say we want to go down to 512 dimensions. Well, so if we didn't care about meaning too much and we just wanted to do sort of dimension reduction, we could do what's called hash encoding, right? There are ways that we could encode everything so that it's just smaller and it's more densely packed. And, you could almost imagine that rather than associate each word to a one-hot vector, you could associate it to a random number of a fixed length. So, between, 1 and 100,000 as a number, and then it would just be like, random. So it would each of the digits would be more or less populated, and then you could use that as a representation. Like each digit would be a dimension, with 700 digits or something like that. That would be like a hash. It's a little bit more technical than that because you want to, but essentially you're spreading it all out so that they're all kind of equally far apart. It's not like that representation is at integers because it's not one dimensional. It's, let's say, 200 dimensional. But it still has this problem that like words that are related aren't close together. Still, you will see this hash encoding used sometimes, so keep that in mind. Okay, so this does kind of pack them in densely as opposed to the one-hot encoding, which is sparse. But we don't have this words which are related to each other or close together. And we don't have like directions in this space being interpretable. So you could imagine you could do like principal component analysis. Maybe that would help. You could start with a corpus like news stories, and then do one-hot encoding, and then do, some bag of words, then do PCA, and that might be something, but it would just pick up like the words that are the most variable words, right? Because PCA is basically sensitive to the things that have the most variation, and it doesn't really group things that are related to each other. It would just sort of like focus on the things that vary the most. So that's not going to help us too much. So there's this paper called Word2Vec, which was very influential in terms of word representation. And to understand how it works, we're going to be talking about generative models at some point in the not too distant future, but it's kind of helpful to think about these at this point. So let's say that we have a vector input, and we want to represent it like in PCA by a small code, by a much smaller dimension. So what we could do is we could build a neural network where it starts out with a huge number of input nodes. Let's say it's kind of linear layers. When I say linear layers, of course, I do mean that there'll be nonlinear activations, but just sort of dense layers, not convolutions or whatever. But it could have convolutions. So it starts out with a lot of inputs, and it gets smaller and smaller and smaller. And then in the middle, we have a layer that only has a certain number of nodes. Maybe, 500 nodes. So we went from 80,000 down to 500, let's say. And then we have a bunch of nodes that take those 500 and try to kind of go up and up and up till you get back to the original size. So the output and the input, the number of nodes that are output and the number of nodes that are input are identical. And so this is the architecture. And this is called an autoencoder. If you sort of challenge this particular architecture to solve the following problem, and the problem is, if I give it this input, I want it to represent this output exactly. Okay? So that seems strange. Like why are you training a network to reconstruct whatever you gave it? But the trick is that we had this bottleneck, right? So the input had like 80,000 dimensions, but the output has 80,000 dimensions, but we're only allowing it at some point in this network, it's only going to have 700 numbers or 500 numbers. I think I said it could be 200. You pick the number. So it has to reconstruct that long vector from a tiny number of, from a very small amount of data. And that is forcing it to do dimension reduction. So that's the idea of an autoencoder. So if you gave it a huge corpus of things and then you forced it to keep reconstructing it, it would start to learn something about the pattern of the data. And it would need to in order to do a reconstruction. Of course, it's not going to be perfect because there's some data loss, but it will learn to do it as best it can. So how are we going to do this with words? Well, remember we had this look before you leap. So we know that the structure of words is, that the missing word that we want to fill in is somewhat determined by the words around it. So why don't we build a neural network whose job is to fill in the missing word? Okay, so it starts out with, like a representation of words, which are 80,000, and actually it has bigger input because it will have a slot for each of the neighboring words. And then it'll have a tiny little part of neurons. And then from those, it will have to predict the missing word, let's say. And this is called the CBO model, or continuous bag of words model. So again, this is not the original paper, but this is a really good paper to explain how word2vec works. So there's two models. One of them is the CBO model, which I'm going to describe now, and then there's another one which is called a skipgram. So it's a shallow neural network. It's not a deep neural network. It's not like the autoencoder I mentioned, which would have many layers. But it's actually just a very shallow layer. And each of the inputs is represented, say, by the one-hot vector. And then you add them all up with some weights. And then it's supposed to try to predict the one-hot vector, which is the output. So it's got one hidden layer with some activations. And it goes in. You input all these things. It does the prediction, and then it outputs. And so you have a huge corpus of text, like Wikipedia or something like that, all of it, and then you basically hide. You go through it and you hide one word at a time. Take a context window around that word and train it to predict the word that's missing. That's the CBO method. Now, a skipgram actually is kind of the opposite, which is, and this seems kind of crazy, but of course, with enough words, you could try to train it. what you're doing is you're starting with a word, and you're actually trying to predict the words around it. Okay, so the skipgram is predicting the words that appear nearby that word. Okay, so either way, you're going to have this hidden layer with n dimensions in the middle. And when you think about it, so let's say you've trained this model. We don't really care that it's predicting these words. What we're interested in is that middle layer. So after it's been trained, after the model has been fit, right? If we pass in a word, in this case, through the input layer for the skipgram, right, it'll run through the weights, and then it'll do the activation, and we'll get the activation at this hidden layer over here. And we are going to take that activation as the code for that word. So that activation now is like 500 dimensions. We went from 80,000 to 500 dimensions. And so we'll get numbers all around those, and that'll represent a vector that will represent that word. If we do this one, the CBOW, it's a little bit more complicated, because what we'll do is we'll have to kind of find the activation for the prediction. So it's a little bit backwards, but in any case, we can get an embedding out of either of these. It turns out that the CBOW works better if you have a small corpus, and the skipgram works better if you have a large corpus. And there's some other tricks that come into getting this to work. Negative sampling and hierarchical softmax. I'm not going to really go into those. But you can read about it in the Word2Vec paper. So how well does this work? Well, it works pretty well. It's pretty interesting that if you've got like a 500-dimensional space and you train the words in, let's say, Wikipedia, maybe the top 10,000 words in Wikipedia or something like that, 20,000 words, it has a really interesting structure. So, for example, the vector associated with, if you take the vector associated with king, and the vector associated with man, and a vector associated with woman, and you subtract man from woman, so that's a vector from man to woman, and you add that vector to king, you'll get a new vector, right? And it'll be a vector in a space. And we don't know what word, it does not need to be a word, but we could look for the closest word. So you're basically forming this vector, so woman minus man, adding it to king, and that's a vector in the space, and then looking for the nearest word that is closest to that. And it turns out that that's queen. So interestingly enough, this embedding, this Word2Vec embedding, encodes sort of a gender thing, right? A change from king to queen, or from waiter to waitress. You did the same thing, you'd actually find waitress. Or walking, walked. So, like a tense, you could then add that to swimming and find out it swam. You could find, you could play with this model because it's in Spacey and GenSim. You can do things like Washington, D.C., America, and then, Spain, and then you get Madrid, So this is a cool project. Sorry, I need to do this for the moment. So this is the word to. This is the 10,000 words in Word2Vect, and this is just PCA. So you can see that the PCA doesn't really tell you much, although you can see some relationships here because it is the Word2Vect. So disk, protein, optical disk, compression, graph. They're somewhat related. But Tisney gives you a better representation of how it looks in this 10,000 dimensional space. So actually, the space is not 10,000 dimensional. I think the space is it's 10,000 words, and it's a 200 dimensional space. So what you're seeing here is a visualization of this 200 dimensional space where these words lived after you doing the Word2Vect algorithm. And this is just Tisney is a good visualization that will keep words that are close together in the 200 dimensional space close together in 3D so that you can kind of understand them better. And you see it's kind of clumpy, right? So in this 200 dimensional space, these clumps are are words that are close together. So we can look at them. We can see those words: few, dozen, thousand, 80, 100, 50. Okay, so those are numbers. Henry, Michael, Jean, those are names. FR, DIE, Des, La, not sure what these are, maybe countries, BI, abbreviations for countries. Della, Leonardo, these are names, obviously. Chile, Cayman, Venezuela, Guyana, Gabon, Eritrea. Okay, these are countries. So what is this showing? It's showing that just by using the some corpus of text, I think it's Wikipedia, and just matching words that are close to each other using this, CBOW model, or skipgram model, you can build a representation of the words where similar words are close together. And these are now much more useful representations of words or of tokens. We're doing this at the token level to present to our deep neural network as a pre-processing. So this is going to be our key language representation. Okay. Oops. Okay. So besides Word2Vect, there are other word embeddings. There's Glove, Fast Text, Star Space, and Elmo. You can, and people do embeddings for all kinds of things. There are image embeddings. There are music embeddings, and these word embeddings, as I'm gonna talk about in a second, then become your keys for the vectors that you start inputting into your RNNs. Okay, so let me stop here for part 2, and we'll have a part 3, and then we'll be done for today.